welcome to the last session of this forenoon. And Chandan will continue with his lectures on extremized sets for Fourier restriction to parabola and cubic monomial.
Thank you. As before, please, if you have any question, please do not hesitate to interrupt. Restriction. It's not restriction. Okay. So last time we discussed how we got these ranges, and P equals 1 is the trivial case, and we're starting to talk about the idea of the proof. So the plan of the today's talk is there are basically 4 steps in proving this. So first we'll discuss this, and then we'll see what's the difference between the cubic monomial and the parabola. Okay, so we started with step 1, and we'll give a sort of very brief sketch of the idea. So the method, the first step is reduce any f in LP of lambda gamma to a finitely many pieces, to finitely many pieces, each of which is adapted to intervals. Meaning, give it any f, I can write f as f1, let me call this f2, and so on. Let's say f10 or f100 plus, let's the remainder r100, r depends on f, so that f1 is supported on an interval of, let's say, tau 1, and so if k is supported on tau k, so if k is basically f, essentially f times, you restrict f to an interval tau k intersection, where f is the height, the length is tau k, the base, and the height is at most about length of tau k power minus 1 over t. So this is at most about 2 per k times the F1 measure of tau k or minus 1 over p times f lambda gamma. Okay. And the remainder is small. So the Fourier extension of the remainder R10, let me call this, yeah, R100, for example, is little of 1, meaning that if we replace 100 by k, this goes to 0. The LQ norm of this goes to 0 as k goes to infinity. As you take more and more pieces, deduct more and more pieces, the remainder has very small Fourier transform. So we don't care about that. Basically, you can talk about the first few pieces. Okay. Okay, so how do you get that? So so the sort of model example that we should keep in mind that we have seen last time is basically FK looks like one of these NAP examples. Each FK is sort of like a NAP example. How do you get that? So the basic idea is adaptation of bilinear to linear argument to linear of tau Vargas Vega. Vega for the paraboloid. I think it was from 1998, coupled with Whitney decomposition. Plus some additional works in higher dimension. Okay, when d is bigger than 2, but so in this case, we're looking at in R2. Okay, so what's the idea here? So first of all, okay, so the first idea is that what we are trying to achieve is this is R2, and we are looking at the Fourier extension of f. So what we're going to do is we're going to look at the diagonal y equals x, and we are doing the decomposition. What I mean by this, we're looking at finite overlapping collection of rectangles, not rectangles, I would say cubes or squares, that in this case, if the size that if the length is r, then its distance from the diagonal is about r. Okay, So we can do that. And so what's the idea? So now the idea is that if we do that, we get, so what is happening here? This is another rectangle and this is another rectangle and so on. As you can imagine, as we move farther and farther away from the diagonal, the rectangles, the squares becomes larger and larger. Okay, so this is the Wheatstone decomposition, and what this tells us is that the Fourier extension of f, the LQ norm, let me do it properly. LQ norm square is about sum of these rectangles of squares of Fourier extension to f. Now let me call this. This is interval is I1. This is cross I2. I1 and I2 has same length, and they are also actually disjoint from each other. So this is length 1, this is length 1. So they have one. They are one separated from each other because of this distance from the diagonal. Okay, so x sub r LQ by 2. Okay, so upside. We call this I1. Fourier extension to I2, I1 and I2, LQ by 2. Okay, so now why is that useful? Now, instead of looking at all other possible scenarios, we're only looking at the product of Fourier extension, where the support of the functions are sort of far from each other. And this is where the bilinear to linear argument of Tauberg's comes into the picture, which is the following: that we have a collection of intervals in R2. So you have to get two intervals, so let's say length 1, and another interval of, let me call this I1 and I2. This also has length 1, and they are one separated from each other. Then if you look at the Fourier extension to this, let me call this F1 piece, and this is F2 piece, gamma F1, F2, LQ by 2 in R2 is bounded above by F1, FQ by 2 prime in R, this is in R, and F2, LQ by 2 prime in R. So now if you scale this back to this length and put it back here, we get that what you get is the following. We get something like this. This implies that extension of gamma f LQ is at most supremum over all interval psi, and I have this property that the Affern-Ackland measure is constant on I. So y is not too large or too small, and okay, times, so, and n positive integers, 2 power minus n over capital C, some large number C times. If you restrict f to this interval as function of I, intersection f is at most 2 power minus n, 2 power n times lambda gamma I power minus 1 over p times f LP lambda gamma. LP of lambda gamma times f LP of lambda gamma. Okay, let me write it properly. So the theorem is, suppose that Q equals 3p prime and 1 less than p less than 4, then there exists theta in between 0 and 1. So theta will depend on p. It's strictly between 0 and 1, such that this is this. Okay, what does it tell us? That if, now imagine that this is large, right? This is close to large, and there is an interval on which this is large, which means I can replace on this piece where if we restrict f to that interval, where f is not too large, then this has a lot of LP mass. Remember, as n goes to infinity, this goes to 0. So we can assume that n is bounded. So if is about, if is on this interval, if is about 2 power 10 times the the length of the upper Markov interval bar minus 1 over p. And that's how, so if you look at the first interval, which maximizes the equality, and take that to be F1, subtract F1 from F, and apply the same procedure again and again. And that's how we get these nap type examples, F1, F2, and F3, and so on. Okay, so that's that. So step 2 is, okay, so that's the, I promise that's the only kind of technical part of the argument. Now it's mostly geometric. Okay, so what is step 2? So now let's say we have a sequence Fn, extreme magic, right? So in this procedure, I can write Fn as Fn1, Fn2, let's say Fn10 plus some small a, right? So let's just consider the first 10 terms. Now what happens is that it turns out that the sort of limiting behavior of Fn1 would imply what happens to the other Fns. In particular, so let's say Fn1, remember Fn1 is Fn times characteristic function of an interval tau n1 intersection, where Fn is at most, let's say, about the Fn Macron measure of this support power minus 1 over p. You can assume that each Fn has LP mass 1 and they are extreme magic. Okay. So now there are two possible scenarios. Remember, we know that the Fn measure is constant. So tau n1 can be too large, so their length is bounded. So there are two scenarios. One is that this length does not go to 0 and they goes to 0. Okay, so now this is where the proof breaks down into 2 parts. Let's first consider the parabola case. So case 1. Look at the parabola. It is square. Okay, so what are we doing? So we have an interval sum here, tau n1. If we supported on this, parabola has two symmetries, as Diego talked about. This as gliding symmetry or Galilean symmetry. So we can translate this, glide this along the parabola so that it is based at 0. Meaning, so for any, let's say, t plus 1 square, this is a point on the parabola. This is, we can compute this, t square plus 2t plus t comma t to t plus t square, I believe, plus 1, 1. T plus 1, t square plus, yeah. So I can write this as, well, 1, 0, 2, 1, t square plus 1, 1. So any point, so if you any point on the parabola, the point, there's nothing special about 1 here. So if I replace 1 by t naught here, you see that this identity holds. What it means is that there's a fixed linear operator of volume preserving operator plus a translation. So this is a affine map of R2 which preserves the parabola. Meaning that no matter where the center is of this interval, I can always translate back to 0 and this will preserve the map. Okay, so that means that tau n1 basically looks like, for the parabola, we can assume this is essentially 0 to some epsilon n1. Let me call this as epsilon n, right? Now, there is still this possibility that it might look like this. This is epsilon n, and if it goes to 0, the first piece looks like height minus 1 over p, which blows up, right? So there is this possibility that it might still blow up. I'm talking about only the first piece. Forget about the original function. And now we're going to use the scaling symmetry. Parabola is also invariant under anisotropy scaling given by lambda x, lambda square y. Meaning now I can sort of scale it back so that the first piece looks like the characteristic function of an interval. So after all this, we can assume that tau n1 essentially the just the interval 0, 1. Meaning that the first piece of the function, each function fn, which has, so fn1 has this property that each fn1 is large. So fn1 LP lambda gamma is about 1 over, let's say, a billion for each n. So this is significant for the LP mass, and we know that for the parabola, this sort of looks like characteristic function of Z. And this immediately tells us that now fn2, fn3, fn10, none of them can blow up. Each of them has to look like characteristic function of Z. Essentially, passing to a subsequence, each fn2 each fn3 looks like same function again and again. And that sort of gives us the extreme. Okay, so why is that so? So what are the other possibilities? So this idea was introduced by Michael Christ, as far as I can say, I think in 2012, where he was studying the similar questions for averaging of the paraboloid. So what is happening is that, so one piece looks like this. This is Fn1. Okay, let's look at Fn2. So there are two possible scenarios for Fn2. Either it is fixed, it looks like Fn1, that's what you want, or it can blow up, or it can shoot up to infinity, right? So let's look at the blow up part. So let me call this tau n2, which is the support of Fn2. Now, if this blows up means that the length of tau n2 goes to 0 and Fn2 looks like this. So this is minus 1 over. What happens here? So these two functions have division supports. Now let's look at the Fourier transform, meaning let's look at the Fourier extension. This is a fixed function, so its image looks like basically a characteristic function of a fixed rectangle. Now if we look at this piece, this its Fourier transform looks like, this is about, let me call this delta n, this height to be delta n, let's say. This is about delta n, so this is delta n inverse, and this is about delta n power minus 2. And what's the height? Well, this better be bounded in LQ, so its support is on this rectangle, and the height of the Fourier transform at this bigger rectangle is about delta n power 3 over q, which goes to 0 as n goes to infinity. So now if you look at the interaction between these two pieces, the interaction is supported on this, whose height is very small, so the interaction goes to 0, meaning if you look at the Fourier extension to Fn1, which is a fixed piece, times the Fourier extension to Fn2, which blows up, if it does blow up, and if you look at the LQ by 2 norm in R2, this is about delta n power 3 over q, which is the height, times the characteristic function of this fixed, let's say 0, 1 cross this rectangle, LQ by 2, which goes to 0. So these two functions have division supports on the frequency side. The Fourier extension also have division support essential on the Fourier side. That's not possible. If I want my function to optimize this inequality, that's not possible. And the heuristic is that P is less than Q. This is called strict convexity. So I'm not going to give the formal proof, but the idea is that it's not possible to maximize x cube plus y cube over x square plus y square equals 1 unless for the trivial case where x, y is 0. Either x is 0 or y is 0, otherwise this will never obtain the optimal point on this unit circle. That's the whole idea. Because P is less than Q, this is exactly why we cannot have functions which can be decomposed into two pieces where they have division supports on the frequency side and their Fourier transform also have division supports. Okay, so that tells me that the second piece cannot blow up, right? Because they have division support. The interaction of the Fourier extension LQ by 2 norm is going to 0. Okay. So what's the other possible scenario? The second piece also shoots up to infinity, but the similar argument you can prove that the same thing happens. The interaction also goes to 0. So the only other scenario is that, well, Fn2 has to look like similarly for all the other pieces. So what we have done is that for the parabola, just because the first piece is characteristic function of an interval, all the pieces are also characteristic function of intervals. Okay. So what do you do with this? So Fn.
Chandan.
Yeah. Yes.
That is not very clear because you are saying that maybe you are telling something else.
Okay.
You are saying x cube plus y cube cannot be maximized over the circle, no? Unless x is equal to 0. But
Yes.
I'm confused because a compact set and clearly, so you may be telling something else there.
Yes, I'm saying unless xy equals 0. So I'm deleting this point. If I delete these 2 points, the optimal is not bounded here. It has to be here or here. These are the trivial points. If I look at the unit circle, where is this maximal optimized? Either here or here or here or here, which is the trivial cases. One of them has to be 0 for this to maximize on the unit circle. What I mean by this, x cube plus y cube is strictly less than x square plus y square unless either x is 0 or y is 0. Right? And you can think of x as the first piece and y as the second piece, is exactly what's happening. And 2 plays the role of p and 3 plays the role of q. Yeah. Okay, does that make sense? So the maximal supremum of this is accent on these 4 points. So if I delete those 2 points, those are trivial cases, because I'm assuming that those 2 cases have non-zero LP mass, right? So that's what possible. Okay, so now we have reduced to Fn2 what basically looks like this. So there is an interval first piece 0 to 1. There is another interval tau n2, which is basically another fixed interval, right? It cannot shoot up, blow up. So same interval. There is another interval, and my function, the first piece, looks like this, and the second piece may look like this, and the third piece might look like this, and the fourth piece might look like this, and so on. But right, so this is Fn1, this is the graph of Fn1, this is the graph of Fn2, this is the graph of Fn3, and so on. This is the graph of Fn4. Okay, so life would have been so much easier if we can just assume that each Fn is non-negative, because we have now bounded functions, and each of them has LP mass 1, and so they have a weak limit, and because non-negative functions cannot have 0 weak limit, right? The problem is that the Fourier extension operator is not a positive operator, right? So the thing is that it might happen that, okay, so what's the natural enemy? The natural enemy is that, what my goal is the following. Goal, find a weak limit of Fn, weak limit, so that integration f is not 0. That's all you want. Remember, the end goal is I'm trying to find extreme major f, right? So we better make sure that there is a non-zero weak limit. But it might happen that it oscillates too much. Okay, so we just cannot replace Fn by the absolute value of Fn, because Fourier extension operator is not a positive operator. So what do we do? And it turns out that this is a sort of real possibility. Okay, so the natural enemy, let me give you an example of what's happening. What's the natural enemy? We might have a sequence which is, let's say, supported on the interval 0, 1, and it is at most 1, absolute value is 1, but it still can convert weak to 0. And this is one of the examples is Ramanujan basis. Meaning, take the interval 0, 1, and let's say this is 1 over n, this is 2 over n, and so on. This is n minus 1 over n, and my function is 1 here, minus 1 here, and then 1 here, minus 1 here, and then minus 1 here. So this is my Fn. So this is 1, and this is minus 1. And as you can see, as n goes to infinity, this really converges to 0, right? So I'm not saying this is an extreme sequence. It might well be possible that this is an extreme sequence, right? My function looks like this, although they have complex support and they have uniform bound, but they just oscillate too much to have a non-zero weak limit. So so it sort of looks hopeless, but the good thing is that modulation is just symmetry for the Fourier transform. Okay, so what happens is that, so let me give a sort of example what I mean by this. Suppose I have this function, which is 1 on 0 to pi, and from pi to 2 pi, it's -1. Right? But so, okay, this has L1 mass, the average is 0. But if I integrate this by sine x, so integration, what is f of x? Let me call this f of f. What is f of x sine x? Well, the graph looks like now 0 and then 0. Right? If I multiply this by sine x, this is positive and sine is negative here. So if I multiply negative by negative, it gives up. Now, this is positive in fact, meaning this particular function has f hat 1. So e power I x f of x, which is f hat at 1, is non-zero for this particular x. And as you can imagine, same argument applies here. In fact, for this fn, you can see that e power 2 pi I nx dot gamma t fn t, we convert. So for this particular fn, the Rademacher basis, if I take e power 2 pi I x n x, this converges to some f weakly, where integration f naught square is not 0 anymore, because we do the same trick here. So if we take the this as period 1 over n, so positive says positive and it maps negative to positive again and negative positive again, so we get a positive mass altogether. So that's the idea. So this is the sort of basis for this particular case. It happens that this same idea works here for any particular sequence, although it might oscillate again and again. The same idea works here, and this is known as the profile decomposition. So let me write the profile decomposition. So theorem. Okay, so I'm not going to give the, but this is a white lie. So what the theorem is, suppose we have a sequence fn which looks like this. Suppose we have a sequence fn which looks like this. So each fn is bounded, let's say from 0 to 1, support bounded support, and it's at most constant. So it's at most 10, supported on the union interval. Then I can write fn as a fixed function phi1 plus, excuse me, I can want, so there exists a set of frequencies zeta n in R2 and a fixed set of profiles phi1, phi2, and so on, so that we can write each fn as e power 2 pi I zeta n1 dot gamma t times phi1 plus e power 2 pi I zeta n2 dot gamma phi2 and so on. So given an arbitrary sequence of functions, we can decompose it as sum of fixed set of functions, and the only thing that changes at n changes is the modulation. Just imagine this one. This function is fixed, it's just that we are only changing this modulation. So that these profiles have this property. These profiles have disjoint supports. So summation, okay. So they have, these profiles have disjoint supports on the space frequency side, and their Fourier transform also have disjoint supports. So what I mean by this is that if you look at the extension of gamma of phi j, look at the LQ mass in R2, look at the Q sum, take the sum over j from 1 to infinity, there it might be possible that we have infinitely such profile. I mean, you know, we extracted one and then we subtract that from there and then do this process again and again. Then this is the operator norm because we started with an exponent 6. So let me call this lim sup n tends to infinity extension of gamma fn LQ power Q. Okay, and the second thing is that they also have disjoint support. So summation Pj LP lambda gamma power P j from 1 to infinity is also less equal to 1. Now it turns out that, okay, so if this is literally P, then that basically means that they have disjoint supports, which is not really true because they might have sort of overlap. What happened? Yes. Yes, so they will not have disjoint support, but it turns out that just a little bit, yes. Just for any sequence. This is valid for any sequence. For, yes. So that's what I wrote lim sup of n infinity. And so, but so let me lim sup n goes to infinity, Fn LP lambda gamma. Okay, so power P. Now, if you have P, this is too much to expect. This basically means that essentially if you have disjunct supports, but as you have seen, they will never have disjunct supports, but almost true. So what happens is that this is true where P tilde is not P, but maximum of P and P prime, which is less equal to P, but it just happens to be strictly less than Q, which is what we want. Okay, so what this means is that pictorially, we started with this sequence of function Fn here, which has compact support, which are uniformly bounded pointwise. We wrote it as sum of fixed set of functions, and only the modulation changes. And this fixed set of functions has this property. Phi1 looks like this fixed function, Phi2 looks like this, and Phi3. So let me call this Phi1, Phi2, Phi3. And if you look at the Fourier transform of these pieces, they look like this. They also have disjunct supports. So this is extension of Phi1, this is extension of Phi2, this is extension of Phi3. This is in R2. Again, that's not possible because remember, by strict convexity, if we have any hope of having an extremizer, if this Fn was extremizer, that means forget infinite many, that means that if you have Fn is extremizer, then we have only one profile and everything else is just zero. Just for the same reason here, strict convexity. So if Fn is extremizing, then in fact, P1 carries all the mass. P1 LP lambda gamma is actually 1, and therefore Phi2 is Phi3, everything else is 0, almost everywhere. Which means, in short, the sequence that you started with Fn is nothing but e power 2 pi I zeta n1 is a fixed sequence dot gamma t times Phi1t. Fnt is this plus a negligible error equal to 1, and therefore this must be an extremizer because Fn was extremizer. Okay, so that's the proof for the parabola. So where does this break up? Any questions so far? Okay, so where does this break up when you go to TT cube? Okay, so all right, so we had okay. Now let's go back to the cubic monomial. So the cubic monomial, the first piece has again two choices. For the cubic monomial, remember we can write again Fn as Fn1, Fn2, and so on. And Fn1 is supported on an interval tau n1, right? Now the cubic monomial TT cube is preserved under this anisotropic scaling. Xy goes to lambda x lambda cube y. What it means is that if this is tau n1, I can make sure by scaling that it is based at 1, t equals 1. So I can write tau n1 without loss of generality as something like 1 plus 1 epsilon n, right? Now we can't guarantee that epsilon n does not go to 0 because it has no further symmetry at all. So for TTQ, we have two possible scenarios where, so two scenarios now, two cases is that epsilon n is identically just epsilon, some positive epsilon. Along the subsequence, it's just fixed. So the first bit does not blow up for the cubic monomial, which gives us, just as in the case of parabola, an existence of extremizers, and this particular sequence converges in LP to an extremizer, which is what we have done. Or case 2 is that epsilon n, in fact, does go to 0. In which case, Fn1 looks like, essentially looks like epsilon n power minus 1 over p times characteristic function of 1 to 1 plus epsilon. It does blow up. Yes. Yes, yes, yes. There is no Galilean transformation here. No, there is no replacement. That's the problem. This is the only symmetry you have. You have TT cube is the only symmetry. In fact, for a general polynomial, there is no symmetry at all. So we can't even identify the position. The difference between the parabola and the cubic monomial is that for the parabola, we can simultaneously identify the position and the height. we can control the position at the height, and for monomials, we control the position but not the height. So that gives us a dichotomy. So this is what gives us a. Okay. Again, so now, okay, so what we have is that we have ET cube. So one of the pieces, 1 to, let's say 1 to 1 plus epsilon n, the first piece blows up. This is the possibility, right? So this question is now what happens to Fn2? It turns out that Fn2 must blow up. If Fn is extremizing, Fn2, Fn3, Fn10, everything has to blow up. Fn2 cannot be, first of all, Fn2 cannot be characteristic function of set, just by the same argument here we had, right? I erased it. So Fn2 has to blow up, and it also cannot go to infinity, shoot up to infinity. So all of this has to blow up. So the question is, can I have arbitrary delta functions? Basically, think of it as a delta function as n goes to infinity. Can I have arbitrary delta functions giving us the maximum possible energy? And it turns out that no, we can't. The only other possibility that Fn2 has to blow up at either t equals 1 minus 1 or t equals 1. All the other Fn's are have to blow up either at t equals minus 1 or 1. So what's happening here is that, suppose what's the idea here? So let me sort of simplify this a little bit. We will come back to this example. So what we are really asking ourselves is the following question. Suppose you have a pond and you put something here, you drop a pebble here. So it creates one single wave packet, right? And so the question is, so let's say this is the wave packet for one pebble dropped here. The question is, can I identify another position so that if I drop another pebble somewhere, when the meet, they do not diminish each other. In the meet, they make a bigger splash, right? This is what we are asking. And so the intuition, our intuition says that that's possible only if the other pebble is here, so that when they meet, they make a bigger splash. If the delta mass is here, the other one has to be delta at the north pole, so that the Fourier extension, if you look at the Fourier extension of these pieces, they overlap a lot. That's the intuition. And this was first observed by Frank Leib-Sabin for higher dimensional sphere for SD, because then, so this was Frank Leib-Sabin in 2016, I think, for SD, sitting in RD plus 1 for the Stickers estimates for the unit sphere for d bigger than equal to 6. They proved that the only other possible, the only obstruction to P compactness is couple of delta functions at the north pole and the south pole. Okay, so the question is, what happens for a general sort of figure like this? Well, it turns out that stationary phase tells us exactly what's happening. So what is this? So if I look at this one, so if we look at the Fourier extension of this space, this looks like something like this. This is, let me call this epsilon n. So this is epsilon n inverse. This is epsilon n power minus 2. And then if we take any other point, this will give us another. So the question is, let me fix this point T naught, for which T naught this intersection will be quite large. That's the question we are asking. Okay, so it turns out that this is because of stationary phase, and it turns out that there is a simple algebraic identity which expresses this condition, and the algebraic identity is the following. For any T, let's look at the torsion matrix, 2 by 2 matrix given by the first column is the derivative and the second column is the second derivative. So in this case, we are looking at TT cube, so 1, TT square, 0, 60. In this case, so we have assumed that the first piece at t equals 1. So at another point, we have another blow up gives us bigger energy if and only if. So this happens. So the only way two delta functions will give us bigger energy is if they look like this. The intersection looks like this. They have to be parallel to each other and they overlap a lot. And this happens if and only if we look at TT0 inverse. So this is the blow up at T0 and another blow up is at T equals 1. The first piece times T at 1 is upper triangular. So these are 2 by 2 matrix whose 2, 1 position is 0. So we can, this is simple matrix, so we can calculate this. Okay, so so 1, 0, 3T0 square, 6 T0 inverse times at T equals 1, which is 1, 0, 36. Well, if we calculate this, what do we get? We get 1, 0, 1 over 60, right? And then if I divide, so this is minus T naught over 2 and multiply this by 1, 0, 3, 6. And so all you are interested in this position, what do you get? Minus T naught over 2 plus, so we get minus T naught over 2 plus 1 over 2T. Is it 1 over 2T? Yeah, 1 over 2 T naught. So you want this to be 0, if and only if T naught square is 1, if and only if T naught is plus minus 1. So for the monomial, for the cubic monomial, either all these pieces, Fn2, Fn3, and so on, either they blow up at T equals 1 or T equals minus 1. That's the only possible scenario. So now we have reduced our arbitrary extremizing sequence to a couple of blow-ups, T equals 1, T equals minus 1. Yeah, so, but we already scaled, right? We made sure that one of them is 1. So the first piece is based at 1, right? So if the other one is at 2, that's not possible. It can be at least at most at minus 1. That's the only possible scenario. Yeah, you're sure. So 2 minus 2, but you can just scale it back to 1 and yeah. Okay. So the next question is, how do you deal with these blow-ups? So for that, what we're going to do is, how much time do I have? 20 minutes. I'm sorry? 20 or 10? Okay, thanks. Good. So now what we're going to do is so what we are going to do is so what we have done is that T equals minus 1 is the only possible blow up, and that's the only possibility of the exponential sequence. So what I'm going to do is let's look at one blow up at a time. Let's look at this piece. Okay. So we have this function Fn. Let's look at Fn times characteristic function of P positive. Just one blow up. So what we're going to do is we're going to zoom in on this part of the curve. What do I mean by this? We're going to do a Taylor polynomial expansion. We're going to look at Fn at 1 plus epsilon ns, epsilon n being the length of the support of the first piece, s times, remember Fn is about epsilon n power minus 1 over p. So this is epsilon n power minus 1 over p. Epsilon n power minus 1 over p. Epsilon n power minus 1 over p. So this, let me define this to be capital Fn. What can you say about capital Fn? Well, capital Fn is first of all is compactly supported. So this is supported on the interval 0 to 1, about 0 to 1, and these are also uniformly bounded. Right? Okay, so that's good, but it doesn't help us. But so these are sort of like corresponding to this new sequence. We also have a new sequence of polynomials now. Look at this polynomial. So gamma is the ET cube. We look at this gamma 1 plus epsilon ns minus gamma 1. Look at the Taylor polynomial basically, and look at the torsion at 1 inverse, and look at the epsilon n inverse 0, 0, epsilon n inverse minus 2. So we are kind of pretending that, remember, the torsion at this point is non-zero. So if we zoom in, we expect this to look like a parabola. So that's why we are doing this scaling, epsilon inverse, and the second code is multiplied by epsilon by minus 2. We do this calculation, what we get is the following. S comma s square over 2 plus epsilon n times 0 s cube over 6. Remember, s is now from 0 to 1. Right? What this means is that this sequence of polynomials now, let me call this gamma n, which is a polynomial of degree 3, each of it degree 3, right? This is a degree 3 polynomial, excuse me, converges to the parabola as n goes infinity. It turns out that this is helpful for us because Fourier extension is continuous with respect to polynomials. Meaning, so gamma n converges to the parabola T square over 2. It turns out that if you have a fixed function, so for each fixed f with compact support, so f is bounded, let's say supported on 0, 1, extension of gamma n, f is fixed, convert this to extension of the parabola over 2 to f in LQ of R2 for each q bigger than 4. Right? So what does it say? So we started the sequence Fn blew up, we scaled it back, we got a sequence of functions which are uniformly bounded and has uniform complex support. And if you look at the Fourier extension of this converges to the Fourier transform corresponding to the parabola of this sequence. Now we have an arbitrary sequence now. But now the problem, the thing is that this is not a fixed function. So how do I get a fixed function? We can do a profile decomposition game again with this particular sequence now. We're going to play a profile decomposition game with this uniformly bounded sequence or with compact support. It says that you can replace Fn by S just a fixed function phi1 basically. What it means is that just blow up. So this is nothing but a fixed function phi1, meaning Fn as a function of t positive is nothing but epsilon n power minus 1 over p times this fixed function phi1 at t minus 1 over epsilon n. Because we're going to play with this sequence Fn, and because the Fourier extension is continuous with respect to polynomials, this Fn can be replaced by a fixed function because this is extreme-imaginary. Remember, if it is extreme-imaginary, it must come from a fixed function. And this fixed function will be this one. As you can imagine, this is the extreme-imaginary for the parabola. You can do the same game with the other blow-up. We can do the same game here. For the same other blow-up, we can get another profile, phi2, fixed function, so that Fn times characteristic from t less than 0 essentially looks like epsilon n power minus 1 over p times phi2 of minus t plus 1 over epsilon n. And these phi1, phi2 will play the roles of those extreme edges for the parabola. And it turns out that after some sort of bit more work and some algebra, it turns out that phi1 and phi2 cannot be arbitrary extreme edges. They have to have some with extension of tt squared over 2 to phi1 absolute value almost everywhere, alpha times extension of with respect to tt squared over 2 of phi2 almost everywhere on R2. If blowing up phi1 and phi2 at equals 1 and minus 1 gives us the possible energy, then they cannot be arbitrary. They have to be tilted by this identity almost everywhere. Where alpha is that maximum of that weird function that talks. I think I'll stop here. More questions for more questions and comments. Thank you.
Questions?
Yes. What happens is that so let's assume that one of them is the identity, right? After an affine change, you can assume that one of them is the identity. So one of them is identity. So let's say T1 is identity. So I2 1 0 0 1, right? And T2 is, so that means we want T2 to be upper triangular. Inverse of an upper triangular matrix is upper triangular, right? Right? If a matrix is upper triangular, if only its inverse is upper triangular. So we want T2 to be something like A, B, C, and this should be 0 here, right? Why is that so? What I'm saying is that we can just change the curve. We can do it instead of looking at TT cube, we can look at TT cube times 1 0. What is that? At 3 6, right? 3 6 inverse this curve. It's okay. It's the same thing. It doesn't. These are all affine invariants. I remember we are working with affine Acton measure, so we can do affine change as much as you want. Okay. Anyway, so we are looking at this matrix. So okay, so T2, the torsion at, let's say, at another point T is A, B, C, D. Okay. So the question is, what you really want is that, So let's say this is the curve. This actually works for any polynomial curve. It doesn't depend on. So let's say this is 1. So this is what it looks like, right? This is 1, 0, 0, 1 is T1. And another point, this is about AB, and the second derivative is this about CD, right? So the thing is, so what is the Fourier transform of this piece like? Looks like, if you look at delta neighborhood, it looks like delta inverse cos delta inverse. Is it delta inverse or delta inverse? Let me make sure. Okay. Yeah, sure. Okay. So we're looking at extension of, let me call this F delta being, this is about delta power minus 1 over P, and this is delta. So this is, let me call this G delta. Let me call this G, and this is called F delta times extension of G delta. L, we're looking at LQ over 2, right? R2. Okay. The thing is, okay, so what are you looking? We make a change of variable here. So let me see. Delta inverse. Oh, there is an identity here. Yeah. Okay. There is identity here. So let's say F is, what we are really doing is this. Delta power minus 1 over P, let's say characteristic function of 0, 1, P over delta, right? This is what we're looking at. So, and gamma is the fixed curve, right? So now we're looking at, let me call this F delta. What is extension of gamma at F delta? There is a change of variable which sort of simply translate this to the simple function. So let me do this calculation. 2 pi I x dot gamma t F delta, which is delta power minus 1 over P delta power minus 1 over P times characteristic function of 0, 1 T over delta dt, right? Okay. So now, sorry, lambda gamma at T dt. Let's make a change of variable. P over delta is S. If we do that, we get e power 2 pi I delta power minus, so characteristic function of 0, 1 at S, lambda gamma. So T is delta S. And if so let me define this lambda delta, gamma delta to this function, gamma at, so 0 plus delta, so delta T times, so the torsion is identity, so gamma delta T times torsion inverse times delta inverse 0, 0 delta power minus T. This is the new polynomial. So now what happens is that this becomes lambda gamma delta S, lambda gamma delta at S ds, right? And then how does it change? This becomes 2 pi I x dot gamma t. So T is delta S. So delta S, and then this becomes, comes here. So this becomes d delta inverse. I'm going to explain what I mean by d delta inverse gamma delta S, where d delta inverse is an isotropic scaling. This matrix delta inverse 0, 0, delta n for minus 2. Right? So this by transpose, we can take this to that side. What this means is that this is the Fourier extension with respect to the new polynomial gamma delta of the fixed function, characteristic function of 0, 1, applied to d delta inverse x. Just delta inverse x1, delta inverse x2. By the way, this is how we get the dimension of the parabola, dimension of this rectangle, that this is delta power minus 1, delta power minus 2, just by making this change of variable. This is how we get. Okay. So now, as you can imagine, if this is, so for this, because this was the torsion was identity, now if the torsion was not identity here, what would be the change? What would be, this is T at T inverse, right? So here would be d delta of T inverse x. right? So this should be T of T inverse transpose at this, right? So what we're looking at is this. What we are looking at, extension of gamma delta applied to character function of 0, 1, delta inverse x1. So let me call this d delta inverse x, delta inverse x1, delta power minus 2 x2 times extension of gamma delta tilde. Let me call this gamma delta tilde. The new one is gamma delta tilde, right? At the other point, applied to another characteristic function of 0, 1. Applied to T1 transpose inverse d delta inverse at x, right? Now, if I do a change of variable, what do I get? What are you looking at? We do a change of variable, we get fixed function f. Let me call this f. Let us call this function. So this converges to extension of gamma 0, right? So this is, let me call this f as function of 0, 1. F times g applied to d delta inverse T1 transpose, so T inverse transpose d delta x LQ over 2, right? Now, if this is not upper triangular, you can imagine we are basically, so what is f? F is a single ball, fixed ball. And we are looking at the intersection. So remember, G is another fixed function. So what is this? This is the volume of power 2 over Q of the set, which is a fixed ball of radius 1, times, if we scale the ball, another ball, by this matrix. If this is an upper triangular, what does it look like? This looks like 1, this remains fixed. This is like delta power something. This remains fixed, right? And this is like A over delta, where A is the matrix, right? If this blows up, what we are looking at it is something like this. And so the intersection goes to 0. That's what's happening. Anyway, so yeah. Thanks. Yes, yes. So as I said, the result holds for all polynomial curves. Sorry? For all polynomial curves. For a general polynomial curve, what happens is the following. Either extreme edges exist, or you can strategically place delta functions at a few points, depending on the degree of the polynomial and the dimension, which will optimize your energy. And in that, you can explicitly calculate the extreme edge sequence and calculate the no pattern, just as we did for the TT. Arbitrary polynomial curves, yes. Any polynomial curves, yes. But for polynomial curves, so let me remind you that if you want, so the question is one of the, so let me sort of make it a bit more precise. If the question is it possible to find a polynomial for which 100 delta functions will optimize energy? And the answer is yes. There's a polynomial of degree 1000 probably, for which it is possible to get 100 delta functions strategically placed. By strategically, I mean not arbitrary points, not 1 and 2 in this case. So it has to be 1 and minus 1, for example, for TT cube. So it will depend on the polynomial, but you can put 100 delta functions which optimize the energy. It is a possibility. If it doesn't, then extrema just exists for that particular polynomial, and every single x by j sequence converge along the subsequence and automodulation. That's the idea. And the basic idea is that, so why does it work? Because you see, this kind of argument is very local. It doesn't all depend on the global symmetry. That's why it works. Yes. For the what curve? TT4, yes. For TT4, yes, but bit sharp. Yeah. There is only one delta function. It turns out that if the optimizer doesn't exist, there is only one delta function which is at t equals 1. So if you put a delta function minus 1, this will not optimize. They can easily calculate the actually in this particular case, just calculate the torsion matrix. Look at this this one. So look at T1, T inverse. You can calculate the 2-1 position term. You see that this is upper triangular if only t equals 1. It can be seen very easily if you look at the corresponding support of the Fourier extension of this delta function by stationary phase will tell you that it's possible only when this one. So if this happens, it sort of behaves like this. So the result is the following. I should say now because, okay, we have time. So the result is the following. Okay, for TT square, things are perfect, right? Extremely exist and everything. For T power 2n plus 1 for odd, always have this possibility that there is a delta function 1 and there is a delta function minus 1. For every odd, doesn't matter what number this is. And for every even, T power 2n, there is only one delta function. If extreme major doesn't exist, that's the only obstruction to pre-compactness. And in fact, in this case, you can imagine the norm of the Fourier restriction operator corresponding to these. All of these are just the norm of the Fourier restriction operator for the parabola. And for it's this alpha times this weird number. Then things become interesting. Yeah, then we might have this possibility. There might be, so let's say we look at t square plus t cube plus t power 5. Then there can be at most 2 times 5 minus 1. The only obstruction is that there might be 9 delta functions, which will optimize this inequality or extreme majors exist. Only depends on degree of the polynomial. Yes, and the dimension d. In this case, that's 2. For analytic curves, let me be careful. Yes, they are. One second, let me make sure. Yes. So the question is that how many delta functions can we have? Possibly delta function can we have which might optimize energy will be bounded above. So the number of delta functions is in dimension d. So gamma is a polynomial from R to Rd of degree n. So the number of delta functions which can optimize energy is d times d minus 1 over 2 times 8 minus 1. So you're saying what if capital N goes infinity? I don't know, but it might be possible that we need many.
Are there any situations where there exist no extremizers? I mean, here you're looking at.
Yes, you said one example, right?
The curves.
The first lecture. Yes, there are a lot of functions which will not have optimizers.
Yes.
Ramanujan has the example, right? Where he has, yeah. I'll talk to you later. Yeah, there are quite a few examples where you do not have an extreme. Okay, any more question? Yes, yeah, oh yeah. We always forget.
Any question from online participants? Looks like there is no, so let's thank them.
Thank you very much.